You'll see I've skipped over the example because that actual example that I have in my notes doesn't require the addition of areas. You'll see that it actually requires the subtraction of areas, so it's necessary for me to jump down to the explanation about why and when we will need to subtract areas. So you will see that if ever you have the situation like is demonstrated here, where the shaded area is, again, between two functions, now between them. That is, for the entire region, the red straight line is the top boundary, and the blue parabola is the bottom boundary of our region, the bottom of our region. In that case, it's like we've taken the area under the straight line, and actually that's too much. So imagine the area under the straight line. And if we then subtracted the area under the parabola from that area that is too much, we would have the remaining region that you can see here is shaded. So that is the understanding behind why we are subtracting the areas. So it just becomes, again, a matter of identifying the points of intersection. We only really require the one integral, and so this shaded area or shaded region is equal to the integral from, maybe I should have identified the points of intersection for you. I'll just pause the video and do that. Yeah, that wasn't too difficult, and it's probably what we could have read from the diagram, though we don't ever do that. We always solve the equation simultaneously to find the point of intersection. But yes, it's going from -1 to 2. So we want the shaded region, -1 to 2, of the top, which the top function is this, x plus 2, and we're going to subtract the area under x squared. Now you'll see I put it in brackets there, which strictly speaking wasn't necessary. However, if that equation had more than one term in it, for example, if it was x squared minus 4, it would be necessary for you to bracket it so that you get this subtraction thing right. Remember I said, oh, no, you will hear me say later that the most common mistake is when students, it's not their understanding of what's going on or their understanding of integration and area, it's just their mistake with their arithmetic, subtracting, or their very basic algebra, subtracting more than one thing, really. So keep that in mind, because we will be subtracting areas using subtraction within our integral, then yeah, we have to be careful. And it's with respect to the x-axis, so it's dx. Interesting thing is, you know, it doesn't really matter where these curves sit. So even in the situation where, let me just see if this works. No, it wasn't that one. Here with this one, now the region between the two is this region, the two functions, and you can see some of it's above the x-axis, some of it's below the x-axis, this region. You might be thinking, oh wow, should I separate this because some of that will be a positive and some of it will be negative? Well, the answer to that is no. No. Don't overcomplicate this. It doesn't need to be overcomplicated. In this situation, you will simply do the straight line, subtract the parabola. Again, it's the top, subtract the bottom. And you can see I've written that down here. No matter where the graph is, where the regions sit, the area between curves can always be found using the integral of the top, so that's integral of the top minus the integral of the bottom, or, as you can see I've done here, I've put them together, the integral of the top, the equation for the top graph, minus the equation of the bottom. And when I say bottom, I mean the underneath boundary. So at this stage, I think I will end this video and we'll actually create a third video where I actually do a couple of examples for you.